let's get back to something we used to do first semester, which is give you a video walkthrough option also on this key. I wanted you guys to start making these, but not too many people are biting right now, so hopefully this will inspire you guys to start making your own. Because remember, if you make a key over at least 2 of the problems on any of the homeworks, you get to omit one of those questions off of your test. And so I'll do the first one, but if you guys want to pick up the ball and do make these videos for the rest of the homework, that's just to your advantage. Anyway, let's get into it. So question number 1, they're talking about this polynomial, and we want to use Descartes' rule of signs and the rational root theorem just to make some predictions on what kind of roots or what the roots could actually be for this polynomial. And so you guys did a really great job making these posters that are literally sitting just behind me. So this should hopefully just be an exercise. One thing we can notice right off the bat is that this is a fifth power polynomial. And so we know no matter what we have, we're going to end up with 5 total roots. So this is really just a way of tuning that in and getting more information about the potential roots. Using Descartes' rule of signs, we're going to make 2 evaluations, one in f of x, one in f of negative x, and we're going to just observe what kind of sign changes these functions undergo. So we already have f of x in front of us. I'm going to go ahead and write in f of negative x. So we made the observation in class that if you substitute in negative x for x and run it through a polynomial, only the polynomials, or I'm sorry, the terms with a odd number power will end up changing signs. So in case you didn't catch that, let me go through it once more, just so hopefully you can see this pattern. If not, you can go ahead and skip ahead, because this will just take a moment. Okay, and so if you notice in this f of negative x, if I have an even powered term, and like the second one, for example, this negative x to the 4th power will end up kicking out just as a regular old x, because for every 2 x's, for every 2 negative x's that you have, you end up with a positive x, and so 4 will end up with 2 even pairs, thus canceling all the negatives. That's unlike the first term where we have an odd powered x value. So we can pair up every 2, we'll take those negatives out of the picture, but with an odd number, there'll always be like 1 more negative x. And so the effect on the problem, effect on this term in particular, is instead of having a positive 8x to the 5th, we'll have a negative 8x to the 5th power. The positive powered ones will stay the same, so that's still negative 4x to the 4th. This will be positive 3x cubed, because 2 negatives again make a positive. This will stay negative 2x squared. This will become negative x, and that's minus 4. Now to use Descartes' rule of signs, what we're going to have to do is look at the number of times a sign changes. So if we look at the f of x, the regular positive power one, that will tell us how many, or inform us how many positive roots we have, positive real roots we could have. And if we look at the sign jumps of the f of negative x, that will tell us the negative real roots that we could have. To put that in action, we'll notice that the first term starts out as a positive coefficient, and then we switch to a negative coefficient. So that's going to be 1 sign change. Going from the second term to the third term, it stays negative, so there's no sign change there. To the next term, also negative, no sign change there. But if we notice, we're going to jump to a positive x, so that's our second sign change. And then from positive x to negative 4, that's a third sign change. So what that will tell us, as if we want to know how many possible positive real roots we're going to have, okay, it's going to be equal to the number of sign changes, so it's going to be 3. Now, this is only a possibility, so we do have to account for imaginary roots, and so we could take away 2 of these positive real roots, and they could express themselves as imaginary roots, and so this could also be just 1 positive real root. We always have to account for those imaginary roots. We don't know if we're going to have them, but the whole point of this is just to do some evaluation. If we look at f of negative x, we'll notice we start out as a negative term. It's still negative in the second term, but then we jump to a positive. So that's 1 change. Then we jump to a negative. That's a second change. And then it stays negative throughout the problem. And so if we want to know about the possible negative real roots, okay, we'll notice we change sign twice, so we could have 2 of those. But again, since we have to account for complex roots, or at least possibility complex roots, we could also have 0. Now this meshes well with what we talked about right off the bat. We said it was a 5th power polynomial, and so there could be a total of 5 roots, or it should be a total of 5 roots. And so these are the possible combinations. I could have 3 real positive, 2 real positive, which means they're all real. 2 real negative, which means they're all real. I could also have 3 positive real roots and two imaginary roots. And you can see kind of how it can just kind of be a predictor. But that's, in the end, that's all Descartes' rule of science really is. Now, the second thing we're asked to do is to generate a list of potential rational roots, just using the rational root theorem. So to use the rational root theorem, what we're going to do is two things. We're going to look at the last term, which is a 4, and the first coefficient, which is an 8, and we're going to try to figure out all the different combinations, fractions we can get from that. Remember, rational roots, rational just means can be expressed as a fraction, and so we're just generating. Okay, so the rational root theorem says if we want to generate the list of potential real roots, we have to look at all the combinations of p over q, where p are the factors of the last term, and q is the factors of the leading coefficient. And so this is going to be all the positive and negative factors of 4 over 8. Okay, remember, these are factors, not just numbers, so we had to break up 4 and 8 two different ways. And so to get 4, we could make 1 times 4, we could take 2 times 2, and so our top factors are 1, 2, and 4. On the bottom, to break up 8 into its factors, we're looking at 1, 2, 4, and 8. Okay. So now we have to take all the possible combinations of these top and bottom values. Of course, positive and negative, because we could end up with positive numbers or negative numbers. So we're just going to go down the line. So I'll start at the top. 1 over 1 is 1. 1 over 2 is a half. 1 over 4 is a fourth. 1 over 8 is an eighth. And we'll do the same thing with 2. And so 2 over 1 is a 2. 2 over 2 is 1, which we covered. 2 over 4 is a half, which we covered. 2 over 8 is a fourth, which we covered. And so the last roll is with the 4. And so I'll take this 4 over this 1 to get 4. That 4 over this 2 gives me a 2, which I already have. 4 over this 4 will give me a 1, which I already have. And then 4 over 8 is a half, which I have. And so according to the rational root theorem, these are all potential rational roots, which also tend to be real roots, that we could have this polynomial. Okay, so these are the steps you guys covered last week. This should not be too big of a surprise. Hopefully this is just review. And so now the next step that we're covering today is how do I test those roots. And so it turns out there are 3 different ways that are good to test these, manually anyway. We have polynomial long division, synthetic division, and manual substitution. Excuse me. It doesn't really matter which way you take to solve these or to test these factors or roots. It just has to be one of these 3 ways because these are the ways that we know are analytically acceptable. So let's practice all 3. So I'm telling you right off the bat, x minus 5 is a factor of this polynomial. And so it's just really an exercise in testing to make sure that's true. So the first one we're going to test is polynomial long division. So let's go ahead and set that up. So we have x minus 5 on the outside. On the inside we have 20x to the fourth minus 70x cubed minus 140x squared minus 35x minus 75. So this setup alone should kind of turn you off to using polynomial long division for this, but it's a total viable way. Just keep in mind what we're looking for is this. If x minus 5 is a factor of this polynomial, that means I should be able to divide into this polynomial with no remainder. And so as long as we get a remainder of 0, we're good to go. Anyway, let's jump into it. So let's see. So the first thing I should ask myself is, what do I need to multiply x to end up with 20x to the fourth? And hopefully we'll conclude that we need 20x cubes to do that, because 20x cubes times an x will give me 20x to the fourth. As a result, I do have 20 times negative 5, which is negative 100 x cubes. Okay. So then we'll subtract this line off. So 20 minus 20 is 0, of course. Well, I have a negative and a negative, which makes a positive, leaving me with 30x cubes. Of course, everything comes down to this step, just like normal long division. So of 140x squared minus 35x minus 75. So now we just continue this show. So now we're going to ask ourselves what to multiply x to get 30x cubed. So this is going to be plus 30x squares. So that'll give me 30x cubes here. And then we're left with negative 150 x squares, and that's it for that. Subtracting the line off. 2 negatives, again making a positive, I'll end up with 10x squares minus 35x minus 75. Okay, so continuing with the same rhythm, I'll now have to multiply by 10x to get 10x squares. That also give me a negative 50x. When I subtract, again, we have a double negative in play for the 50x. So it'll be plus 50x, so that'll give me 15x minus 75. Okay? And so here's the payoff. Here's we see whether or not it's really going to be a factor. X times 15 will give me 15x, and then 5 times negative 5, excuse me, times 15 will give me negative 75. And so when I subtract off that final line, everything clears, and that's what proves that it's actually going to be a factor in the first place. They end up with a remainder of 0. So long polynomial division does mimic what we've seen with normal numbers, so it might be very attractive, but you can also see this a lot of work to do. We've been kind of handling polynomial long division all semester, and so it's a nice way to do this, but it's not the only way. And so another way we can attack this is with synthetic division, which you'll see is it's very much a mirror to polynomial long division, except we look more at the coefficients and the roots than we do at the whole polynomial. And so first we establish we're going to dividing by 5, because 5 of course is the root that you get from x minus 5. And then we'll set that up to divide along the coefficients. And so the coefficient of the leading term is 20, then we have a negative 70 here, negative 140, negative 35, negative 75. Let's cut off the top problem here. Okay. And so if you recall the rhythm of synthetic division, we're first going to bring down our first number, giving us something to start with. 5 times 20 is, of course, 100. Combine the lines, we end up with 30. Multiply 5 times 30, you get 150. Combine, you get 10. That gives us 50 here, because 5 times 10 is 50. Remaining 15. 5 times 15 is 75. And that will give us 0. And so again, that's where you see that's going to tell us it's a factor. That's going to be 0. Now, if you compare the time involved, we can certainly agree that division is much faster, which is why it's maybe a more attractive alternative to test these roots, especially if you have multiple roots to test. We do have one more, which is just manual substitution. This is not a bad way to do it either. It leaves a little bit to be desired as far as like speed goes and like retestability, but you could totally do it this way too. If x minus 5 is a factor, that means x equals 5 is a root. Root's the same thing as a 0. And so if we take our function f of x, but we test it for 5, we'll just have to see if it actually gives us a 0. And so we can test it for every value of x. We can substitute in 5. Okay. And when you run this through, say with a calculator, okay, and then run this through, you'll end up with the f of 5 equals 0. And so all these three things mean the same thing. They're all different ways to get to the same place. It's completely up to you which way you want to handle that. And so we're going to go ahead and stop the video here for part 1. And we'll jump right back into part 2, where we'll talk about a little bit of stuff we'll do in the future. All right, thank you.